One of the most influential scientists in history, Sir Isaac Newton's contributions to the fields of physics, mathematics, astronomy and chemistry helped usher in the scientific revolution. And while the long-told tale of an apple dropping on his learned head is likely apocryphal, his contributions changed the way we see and understand the world around us. He created the modern telescope. Before Newton, standard telescopes provided magnification, but with drawbacks. Known as refracting telescopes, they used glass lenses that changed the direction of different colors at different angles. This caused chromatic aberrations, or fuzzy, out-of-focus areas around objects being viewed through the telescope. After much tinkering and testing, including grinding his own lenses, Newton found a solution. He replaced the refracting lenses with mirrored ones, including a large, concave mirror to show the primary image and a smaller, flat, reflecting one, to display that image to the eye. Newton's new reflecting telescope was more powerful than previous versions, and because he used the small mirror to bounce the image to the eye, he could build a much smaller, more practical telescope. In fact, his first model, which he built in 1668 and donated to England's Royal Society, was just 6 inches long, some 10 times smaller than other telescopes of the era, but could magnify objects by 40x. Newton's simple telescope design is still used today, by both backyard astronomers and NASA scientists. Newton helped develop spectral analysis. The next time you look up at a rainbow in the sky, you can thank Newton for helping us first understand and identify its 7 colors. He began working on his studies of light and color even before creating the reflecting telescope, although he presented much of his evidence several years later, in his 1704 book, Optics. Working in his darkened room, he directed white light through a crystal prism on a wall, which separated into the 7 colors we now know as the color spectrum: red, orange, yellow, green, blue, indigo, and violet. Scientists already knew many of these colors existed, but they believed that the prism itself transformed white light into these colors. But when Newton refracted these same colors back onto another prism, they formed into a white light, proving that white light, and sunlight, was actually a combination of all the colors of the rainbow. Before Newton, scientists primarily adhered to ancient theories on color, including those of Aristotle, who believed that all colors came from lightness, white, and darkness, black. Some even believed that the colors of the rainbow were formed by rainwater that colored the sky's rays. Newton disagreed. He performed a seemingly endless series of experiments to prove his theories. Newton's laws of motion laid the groundwork for classical mechanics. In 1687, Newton published one of the most important scientific books in history, the Philosophiae Naturalis Principia Mathematica, commonly known as the Principia. It was in this work that he first laid out his 3 laws of motion. The law of inertia states that at rest or in motion will remain at rest or in motion unless it's acted upon by an external force. So, with this law, Newton helps us explain why a car will stop when it hits a wall, but the human bodies within the car will keep moving at the same, constant speed they had been until the bodies hit an external force, like a dashboard or airbag. It also explains why an object thrown in space is likely to continue at the same speed on the same path for infinity unless it comes into another object that exerts force to slow it down or change direction. You can see an example of his second law of acceleration when you ride a bicycle. In his equation that force equals mass times acceleration, or F equals ma, your pedaling of a bicycle creates the force necessary to accelerate. Newton's law also explains why larger or heavier objects require more force to move or alter them, and why hitting a small object with a baseball bat would produce more damage than hitting a large object with that same bat. His third law of action and reaction creates a simple symmetry to the understanding of the world around us. For every action, there is an equal and opposite reaction. When you sit in a chair, you are exerting force down upon the chair, but the chair is exerting equal force to keep you upright. And when a rocket is launched into space, it's thanks to the backward force of the rocket upon gas and the forward thrust of the gas on the rocket. He created the law of universal gravitation and calculus. The principle also contains some of Newton's first published works on the motion of the planets and gravity. According to a popular legend, a young Newton was sitting beneath a tree on his family's farm when the falling of an apple inspired one of his most famous theories. It's impossible to know if this is true, and Newton himself only began telling the story as an older man, but is a helpful story to explain the science behind gravity. It also remained the basis of classical mechanics until Albert Einstein's theory of relativity. Newton worked out that if the force of gravity pulled the apple from the tree, then it was also possible for gravity to exert its pull on objects much, much further away. Newton's theory helped prove that all objects, as small as an apple and as large as a planet, are subject to gravity. Gravity helped keep the planets rotating around the sun and creates the ebbs and flows of rivers and tides. Newton's law also states that larger bodies with heavier masses exert more gravitational pull, which is why those who walked on the much smaller moon experienced a sense of weightlessness, as it had a smaller gravitational pull. To help explain his theories of gravity and motion, Newton helped create a new, specialized form of mathematics. Originally known as fluxions, and now calculus, it charted the constantly changing and variable state of nature, like force and acceleration, in a way that existing algebra and geometry could not. Calculus may have been the bane of many a high school and college student, but it has proved invaluable to centuries of mathematicians, engineers and scientists.